And in this lecture here, let's now study how we can find derivative of logarithm functions. So in my style of teaching, actually, let me put it this way. There are many other professors teaching finding derivative of logarithm function as a separate independent topic. But for me, in my own experience teaching, I find that it's best to teach how to find derivative and how to derive the derivative of a logarithm function after we've learned about, my students learn about how to find derivative of an exponential function. So this lecture specifically, any viewers currently watching this, I highly recommend that you watch my lecture on how to find derivative of exponential function, and then we're going to go ahead and continue here. And then as well as outside of that, I also feel it's best to deliver this lecture here about taking derivative of log function after my students learned about implicit differentiation. And so my bottom line now is that before we can proceed further into this video lecture, I highly recommend that if you haven't seen my other lecture on how to take the implicit differentiation, go ahead and give it a view, and then and also view my lecture on how to find the derivative of exponential function. Then once you have viewed those two particular lectures, then now we can go ahead and proceed into this video. Okay, but now other than that, here we are at being able to find, let's now learn how to find derivative of a logarithm function. So the logarithms. So now for the logarithms function, and allow me not to go too far back of reminding you what a logarithm is, because that was what pre-calculus course is for. So here logarithm is simply at this point here we understand that logarithm is a function. So we can have a log base 2 of x, that is a function. Okay, we can have a function being a log base 10 of x. Okay, and then but then as a worldwide convention, then anytime it comes to log base 10, then we can write just simply the log symbol and skip the base right here. So these are the bases of your log. And as I said, if you're not sure what I'm talking about with logarithms, I highly recommend that you review your skill in understanding what logarithm is all about, because here I'm only going to take the next step, assuming that you already understood you already well understood what a logarithm function is. So these are called the bases, and when it comes to the log base 10 right here, we are skipping the base. We can just simply write log, and mathematicians, people worldwide who study math will understand that this is log base 10. And then another special log right here. So basically anytime we're having a positive number, we can treat that as a base, and your pre-calculus teacher should have mentioned that as well. Anytime we have a positive number, we can create a logarithm out of that base right here. And so the number e that we've learned in some of my earlier lecture, in some of my other lecture right here, the number e is approximately 2.718. Gosh, such a ugly looking constant, just like the pi right here, approximately 3.14 and so on. But even though being not so nice looking, but it's a positive value, so we can use that as a just fine to be the base of a logarithm. And so we define log base e of x here as a short symbol, natural log, ln, as a way to pronounce it, to verbalize it, it's a natural log, ln. So log base e, another way of writing that, ln of x, or the natural log of x. Okay, so these are just some brief, and so generally speaking, outside of the two special bases, base 10 and base e right here, then generally anytime we're looking at logarithm function, then it's log base a of an input argument. That's logarithm base a. Okay, and a here, the base a here must be a positive number, a positive constant. Okay, And so now, before I go on further, just one more brief review, and I promise that's about all the review I need to remind anyone viewing my video. And I'm pretty sure you have seen this as well when you were formally learning your pre-calculus courses. But when we have, what it means being a logarithm is that when we take log base, say for example, if y equals log base a of a number x, so x here is being the input, and for now at our calculus level, we call that this is a function logarithm base a of x. But think about the way how we operate. Then log base a of x to equal this value means the base a. So formally speaking, for calculus students, this equation, this equality is true if and only if, or another way of saying, verbally speaking, it means, so we're saying a number log base a of x equals y means the base a being raised to power y equals x. Okay, so like I said, I only go brief here with this because allow me to assume that you have seen this back in your pre-calculus course, but you do need to nail this understanding regarding logarithm. You need to nail this down before we can advance to the next step and finding and learning about the derivative of these logarithms. Okay, and that's about all it takes right there. That's about all it is. So now, among all the general logarithms, among all the logarithm functions generally regarded by log base a of x, it's just the number e is so special, even though it's not a nice looking number, but log base e will be the one primarily focused as our main target here throughout the entire discussion in this topic. And then from there, we're going to create an extended version for all the general logs later, afterwards. Okay, so now my plan here is we're going to start out studying the logarithms, the derivative of natural log base e of x. So now we're given the function y equals natural log of x. It's a logarithm. It means log base e. Okay, it means a log base e, and we need to find, our goal here is to find dy dx. Our goal is to find the derivative of this given function, dy dx. All right, so let's now put on a final conclusion here. I'm going to take a moment erasing my board here. All right, so what have we learned here? If our function, okay, formally speaking, f of x equals natural log of x, okay, then in that case, then in that way, our f prime here is simply going to be 1 over x. Okay, we made that discovery. All right, so short way of writing this rule, see, the derivative of natural log function. So this prime symbol here is kind of assume the variable here being the x right here. Whatever the variable, the only variable being written in the problem. So natural log of x, take the derivative, gives us 1 over x. That's another way of writing your rule for taking derivative of a natural log of x function. Derivative of natural log of x equals 1 over x. Okay, or a little more formally, see, we have natural log of x, and now when we differentiate, take the derivative of that function. And so as I said, this is an alternative way of writing, but that's quite clear about what variable we are targeting at. The answer is 1 over x. 3 different ways how we can express that rule is like that. All right, so that's how we find derivative of the natural log function, the logarithm base e as a function of x. All right, so now to conclude out an actual formula, an actual rule for for a general logarithm, a log base, any base, doesn't have to be e. So generally, if y equals some log base a, some log base a of x, okay, not necessarily base e, and base e stay in the same rule, but for now I just want to tackle down, the general logarithm derivative for here. So if y equals to log base a in general of x, then if that is so, then the derivative dy dx here equals what we have found here. Let's put it all together. It has that similarity with the logarithm, the natural logarithm, 1 over x. But now, being a little more than the natural logarithm's derivatives, here it's 1 over x, but in the denominator there's natural log of a, the base that originally came with your logarithm. Okay, so that's the derivative of your logarithm base a like that. And so, and then again, looking back at what we have done earlier, see, if we're looking at natural log, if we're blending our rules into what we've learned here, can we treat natural log under this? Can we bring natural log, the derivative of natural log of x, under this rule? Sure we can. See, think about taking this derivative and applying this general rule for general log at any base right there. Then it's 1 over x times natural log of, I'm going to bring base e in here, okay? Because it's natural log is log base e. So if we're applying this general rule for all general logarithms out there into this special natural log of x, it's going to work as well. And what's natural log of e? It's 1. That's why the final answer is 1 over x. It was 1 over x, and now it is again 1 over x. All right, so now for the general, a shorter version of this general logarithm formula is that when you're looking at log base a of x, okay, taking the derivative gives me 1 over x times the natural log of a. That's another way of writing your formula to understand. Or we can also have, alternatively, we can go differentiating in respect to x. Log base a of x, okay, that gives us 1 over x times natural log of a. Okay. 3 different ways how you write your rules for taking derivatives of logarithms, not only the natural logs. Okay. All right, and so now we are ready for doing some examples of logarithm, taking derivatives of logarithm functions. So just like how we learned it in exponential function, the rules for taking derivative of a logarithm, any general logarithm function, is quite specific for the logarithm function. So so no instructor will be giving examples out there that hey, just find the derivative of the simple natural log of x. So those are way too easy, and we have already derived and we've got the problem done. So now again, I have to remind anyone viewing this video that all the basic rules and the product rule, the quotient rule, plus the chain rule, those rules are all I consider as the universal rules. So now in any of these examples I'm bringing up right here, we are about to see a good combination, a good mix of all these rules being blended together in any of my example problem. So let's look at example 1 right here. All right, so we want to find the derivative of, so if the function was written in functional form, once again we use f prime, or if the function was written originally in the equation form, and we find dy dx. Okay, so find the derivative, either f prime or dy dx. So now our first function here, how about given out to be x squared plus 4x, and multiply with natural log of x. Okay, and so what I see here is that we are having a product that existing between this polynomial x squared plus 4x and it's in product with our natural log function. And so now I pointed out and I put in a little dot in red ink right there indicating that. So now we're about to apply the product rule. So product rule says to find the derivative, we must first take the derivative of one of the factor. So the first one to come, so now I'm going to take the derivative of x squared plus 4x. Right? Take the prime of that, and we're going to multiply the derivative of the first function with the other function without derivative. So I'm going to multiply that derivative, the derivative of x squared plus 4x with natural log of x, keeping natural log of x the same. And just like that, we are now, the next part of the product rule says we're going to keep the first factor there the same, but now I'm going to multiply with the derivative of the next function, which is now its natural log of x turn to get taking the derivative. And so now that's how we laid down the product rule and getting ready for real action. And so now when the real action kicks in, f prime now would turn out to be, so the derivative of that, so simply the sum rule is here and the little bit of power rule is here. So I have 2x plus 4, okay, plus 4, that's the derivative term by term for my x squared plus 4x. And now I'm going to multiply with natural log of x, okay. And so that takes care of our half of our product rule. And now we're going to need to add, and so x squared plus 4x is being kept the same here, and now we're going to multiply. So just now we learned about the derivative, specifically the rule to find the derivative of a natural log function. So this standard natural log function is going to have derivative 1 over x, okay. And so now at this point, as far as being able to find the derivative, we're done, okay. We're done. And to be honest, for this function right here, even if you are asked to simplify, there wouldn't be much that we can simplify. So I would call this problem right here right about the end of our problem right there. It's already in its quite simplified form. Or maybe really, if you have to simplify, then you can multiply the 1 over x here for each term right there. Okay, so 1 over x being distributed for each term, but that's about it. So in that case, if you have to simplify it according to your instructor's request right there, or your instructor's requirements, then 1 over x multiplied with x squared plus 4x. And so now, but the first term here looks like there's not much we can do. So there's a 2x plus 4 in product with natural log of x. That came straight out from the first term, but then the next term here, if we combining, if we distributing that 1 over x for each term, 1 over x cancel with x squared, giving us an x plus, and now x cancel with this other x, so x plus 4. And that's about all we can do. And then this is our final answer, which is a little bit more simplified. All right, and so now that is how we have done with part A of our example. All right, so let's now look at part B of the example, example 1. So we have a function, how about y equals, and then here let's look at, let's say, log, so this is skipping the base, so log base 10 over, how about x squared plus 5 here. So what I have here before proceeding into the actual finding derivative, then we can observe that our function here is a quotient. So you see, the big thing that catches everybody's attention here is that we have a quotient. There's a numerator, there's the denominator right here, and then inside of the quotient here, the numerator is a logarithm function, log base 10, and then in the denominator here of our current quotient, then we have a polynomial. And so now in that way, to find dy dx. Having a clear understanding of what our function is, it gives us a good plan of how to handle the derivative, how to find the derivative successfully. So now the quotient rule is what we need first thing in line. So quotient rule says from where our numerator is, I'm going to go ahead and find a derivative for it. So the derivative for log base 10 of x need to be found, and then we're going to multiply that its derivative, the derivative of log base 10 of x, with x squared plus 5, keeping the denominator the same without derivative, and I'm going to subtract. So similar to the product rule, but quotient rule again as a reminder, we instead of adding, we are now subtracting. Now the first term, in the next term, I'm going to keep log base 10 of x without the derivative, but then I'm going to multiply with the derivative of x squared plus 5. Okay, and so that gives us an instruction, a layout for what to do in the next step. And then the quotient rule says further that we need to divide this difference here by the square of your original denominator. So now it's x squared plus 5 being square here in our denominator. And now we are ready for getting the actual derivative. So right now it's just a layout, a foundation for our next step like that. But now let's move on. So the actual dy dx, to really get things completely taken care of, log base 10 of x. So we have learned from and recall for yourself that we have just learned earlier in this lecture that, so now we're no longer in log base e, but we're at some log with some general base. So derivative of log base a of any general base a of x is a 1 over x, but now we need to multiply with the natural log of a, where that a was the original base. Okay, and so now after that reminder, we're going to apply this understanding right here in our example problem. So now this log base 10 right here is going to give me, and of course do not blame it if the expression is starting to get a little more kind of blown up. So this is log base 10, so now our derivative directly becomes 1 over x, but multiply with a natural log of 10. But we keep that as a little fraction, and here I already had a long fraction bar getting ready to complete my entire fraction that came straight out from the quotient rule. And now this fraction there needs to be multiplied with x squared plus 5. Okay, and then we are going to subtract, and I realize that writing it this way is a little too squeezed in right here. So how about I'm going to quickly rewrite that so that we can see more space between the terms right here. Okay, so now I'm going to write it a little bit down below. So 1 over x times the natural log of 10, and then I'm going to multiply with x squared plus 5. Okay, so this came from this was the original denominator of our quotient. And then now quotient rule says we need to subtract, and now we're going to keep log base 10 of x the same, log base 10 of x the same, and need to multiply that with the derivative of x squared plus 5, which is quickly we apply the sum rule and the power rule here. We're looking at 2x, because the derivative of 2x becomes, derivative of x squared becomes 2x, and the derivative of 5 goes to a constant. So now we're just simply multiplying with 2x, and we're dividing all that by x squared plus 5 all squared. All right. And so as far as getting your derivative found, we're done. Okay. But so this problem here, we can spend a little time making the expression a little smaller. So watch out if your instructor is requiring you to simplify the expression, a final answer like this, then here's how we would do it. So I'm going to now move out to my next board right here. All right, so now with our curtain step right there, this is what we have found so far. Let me bring it back to this other board, and you can see. So this term right here is actually all one term, the little fraction 1 over x times natural log of 10 multiplied with x squared plus 5. Now we can write it first of all in one fraction. So let's do that. Okay. So it's now better to write it as x squared plus 5 over x times the natural log of 10. And then we're going to subtract the other term being log base 10 of x multiplied with 2x. Okay, and then we have an overall denominator here, x squared plus 5 all squared. Okay, so that the expression doesn't look any further simplified. Be patient at this point. Okay, so this is not, if we're looking for a simplified, this is not quite simplified yet. So, but now we can make common denominator with these two terms here. So now what I see now is we can combine these two terms in the numerator as one fraction. So now I'm looking at, maybe I need to make a little more space. So I'm going to write it down below a little further. Okay, so we're looking now at x squared plus 5 minus, so I'm going to put the 2x in front of that term. It's a little easier for me to keep track that way. But now I'm going to need to multiply all that here with the extra x times natural log of 10. And then all that now is over a x times natural log of 10. Okay, and we're putting that over x squared plus 5 squared. All right, so a little bit of algebra there again, and now you got a fraction on top of another denominator right there. Then things will all turn out to be okay. So in my next step here, allow me to erase this little part of my board. And so now, continuing from this step, then here I have to write it above here. Then x squared plus 5. Okay, and notice the 2x times and I notice I shouldn't have to have that x squared right here. So there was no square on that x, just that. So this is the step before this. So now minus 2x squared now times log base 10 of x. Okay, but now we can combine these two as one denominator. So all it is now is x times x squared plus 5 all squared and multiply with natural log of 10. But now this expression is at least one fraction. Okay, and it seems a little more simplified compared with the earlier version we have had right here. Okay, but this is a pretty direct answer right out from the box that we got the derivative done. And then in case, my point was, again, in case any instructor is asking you to simplify your final answer, and that's how you were doing that. All right. So now I'm going to bring everyone into the next class of problems where I call that example 2. And so it's still the same kind of problem. We are about to find derivatives. But I decide to put these problems into a brand new examples so that you can recognize another generality here. All right. So let's look at something like this. Question A, how about our function here, f of x equals log base 5, okay, and our function now is log base 5 of 3x plus 1. All right, and so now before we really get into finding the derivative, then we need to observe the function a little more closely. So now the logarithm is base 5 logarithm, but unlike the earlier problems where inside of the logarithms there was only a single x variable, now inside of the logarithm there's the entire 3x plus 1. So we have, what my point now is that we have an expression inside of logarithm, an expression of x being inside of logarithm instead of a simple x variable. So now I start using that term inside again. So that's starting to remind anyone viewing my video about some rule we must bring in as a critical understanding here. And so now inside, I recognize I can recognize, even though again I said there's no right or wrong to recognize who's the inside expression and who's the outside, but in my advice now, in my recommendation here, take this part being inside of the logarithm as your inside expression. And so now with that inside expression, we're looking at the 3x plus 1 to be the inside, and we can assign a new variable names for that. So I'm thinking about we're substituting all that 3x plus 1 as a new variable u right here. And then so now that means after we substitute away, then your outside expression now would become, okay, simply the log base 5 of the variable u right here. Okay, and so now the reason now I start bringing up and start using quite excessively the term inside and outside, because you can start seeing where I'm going in this. We're about to apply the chain rule for these problems. Okay, because anytime you recognize that, anytime that you can recognize that you can take some expression and assign that as some inside variable, and then that means what's left over is called the outside. There you are about to use the chain rule. The chain rule chain the inside and the outside derivatives together. Okay, and so now my f prime now going to become, okay, so chain rule says first we take the derivative of the outside. My outside function is here. Now with my temporary variable is to be the u variable. So it's going to be 1 over, but instead of writing the 1 over u here, how about we're going to write the original meaning of the inside function. So now it's going to be 3x plus 1. So like, as I said, it could have been 1 over u times the natural log of 5 right here, straight out, because recall for yourself, log base 5 of u, when we're taking the derivative, a little bit of scratch work here, if we're taking this derivative, general log derivative is saying that we're doing 1 over u times the natural log of 5. The original base is here inside of the natural log. But now in the actual problem, instead of writing u here, I just wrote down the actual meaning, the actual expression that u represented. And so that's why I'm keeping the 3x plus 1 right here. Okay, so I hope I clarified some of your concerns. And so now I'm going to erase this extra explanation here. But then that's only the derivative of the outside, keeping my expression of the inside exactly the same here. And now I'm going to multiply. Chain rule says we need, after taking the derivative of the outside and keeping the inside expression exactly the same, now I am going to multiply what we currently have with the derivative of the inside. So now go back and locate your inside, what we have recognized, what I have recommended to recognize as the inside is here, the 3x plus 1. So now taking the derivative of 3x plus 1, taking as the derivative. Okay, and so now in my next step, 3x plus 1, taking the derivative is just simply 3. So now what I'm looking at is a 1 over 3x plus 1 in the denominator. And together in the denominator, we have an extra natural log of 5, but now multiply with 3. Okay, and so that's how we're done with this problem. Straight out using, right out from the box, using the chain rule. And again, if you are required to bring your final answer as one fraction, because right now it's one fraction, but multiply with an extra factor here, and we can bring it all together in one fraction. And so you can also write your final answer as 3 over 3x plus 1 times the natural log of 5. This is another way of writing your final answer in case you are required to do so. Okay, so make sure at this point my lecture is one thing, learning from my lecture is one thing, but this is an online class, so anyone viewing this, some viewers viewing this video might not be my own students right here, so to make sure you watch out for your own instructor, see what your instructor is requiring you for the way, as far as the way how you bring in your final answer. Okay, but that was how we have done the part A of our example 2 right here. So now you're starting to see where I'm going. Pretty much the entire, or the rest of example 2 is all about how we can bring in chain rule, because like I said again, back in the day I talked about the chain rule. The chain rule lives everywhere in every problem of ours. All right. And so now I am going to erase. Okay, so all that work now is erased. Let's now look at part B of our example. All right, so part B of our example. So how about y equals so natural log of about 1 plus 2x is not a good one. Actually, I changed my mind a little bit. Sorry about that. This is how about 6 plus 5x plus x squared. All right. So now we have a natural log function, but inside of the natural log function, and as I just said, inside of the natural log function is a polynomial, 6 plus 5x plus x squared. I purposely put my polynomial here in a little bit out of ordinary form here, so that student. I mean, technically, what I'm saying is technically this polynomial, or in a common way, this polynomial looks as following: x squared plus 5x plus 6. But I purposely did this so that we don't have to be too worried about focusing on this standard form, but just simply look at that as we have some expression inside of the natural log. Okay. So now again, I advise, even though you can try exploring to choose different expressions to be your inside expression ready for chain rule to kick in. But now within what I recommend right here, then the inside, I'm going to take all that 6 plus 5x plus x squared, and we can represent that by, or we can substitute that by a variable u. And so then that means once we substitute it away in that entire red underlined expression there as our inside, and we assign that for the variable u, then the outside expression, this is what it becomes right here. The entire expression now becomes so y equals natural log of u. Okay, so that's why this is why I'm calling that outside, because with the outside expression now, all that inside already being substituted away with the variable u, so all that remains is considered as the outside right here. Okay, and so now the chain rule is about ready to be applied here. Okay, so getting into the derivative here, chain rule says taking our derivative, we must first take the derivative of the outside. So chain rule derivative of the outside means taking the derivative of natural log of u. Okay, and we then multiply with the derivative of the inside, which is taking the derivative of all that 6 plus 5x plus x squared. Okay, sort of like I'm writing down a template for that. And then remind yourself that this u right here, because I was short of space, so I should have written that as the u here was that all that 6 plus 5x plus x squared right there. But because I was a little short of space, so I wrote that as a short variable. But now, you see, the derivative of natural log is 1 over u. Okay, but now instead of writing u, I'm just writing the original meaning of our expression inside of u. So 6 plus 5x plus x squared. Okay, and we don't need, so it's the natural log, so we don't need that special natural log of e, because natural log of e equals 1. And now I am going to multiply. These are, it's just a straight old polynomial, 3 terms. So taking the derivative, first term becomes a 0, middle term is a 5, giving me a 5, and the last term gives me a 2x. Okay, so now as far as getting the derivative done, we are done with taking the derivative. And once again, watch out, in case your instructor is asking you or requiring you to put your final answer of the derivative in one fraction. Then here we go, 2x plus 5 divided by x squared plus 5x plus 6. Okay, and that's how we have found our derivative for this particular function. And now I am going to erase this, and let's make space for another example. All right. So I've seen this problem, scattered somewhere here and there among a lot of the web-based assignment problems, including WebAssign, YMath, or and MyMath ML whatsoever. And so here I'm going to bring it out. It seems like a challenge for students, but it's not going to be that bad. So natural log of 1 plus natural log of x. So 2 levels of logarithms. So logarithms of natural log of x. So once again, I see there's a natural log, and inside of the natural log, instead of being one usual or ordinary x, here it's an expression instead of the ordinary x, and that's all I need to point out. So we can regard to this as the inside. Okay, and so the outside now is simply just natural log of whatever that outside is. So let's go ahead and formulate that. So inside is the expression, and this time let me just go a little skippy on the notation here, but just inside here, instead of giving a new variable, I'm just going to get straight to the entire expression as I recommended, even though you have your choice of exploring other ways how you can find the inside here, but I highly recommend stay with this one. 1 plus natural log of x. Okay, and now if that is the inside, and our outside now, our outside is just that natural log of, and all that here goes inside. Well, in the end, it looks like it's always a good idea that we can just use a little substitution there. Okay, so now to get things ready for this, to get ready for our chain rule, then I'm going to once again restate the chain rule a little bit. Chain rule says derivative is first we have to find the derivative of the outside. So the derivative of the outside is going to be 1 over u, okay, because it's just the natural log. So 1 over u, but instead of writing u, I am going to write the actual expression where u substituted for. So it's 1 over u, but u is actually 1 plus natural log of x, okay. So that's the derivative of the outside function. And now I'm going to, chain rule says we need to multiply with the derivative of the inside. The derivative of the inside is 1 plus natural log of x, taking derivative. Okay, so now I just need one more step. So 1 over 1 plus natural log of x, and now multiply. Again, that sum rule is going to apply, meaning we can do the derivative term by term here. So first term becomes a 0, and the next term here is a 1 over x, as we have learned it in our discussion for finding the derivative. And so as far as finding the derivative, and even I am being the instructor of my students, I don't like writing the final answer this way. So I would agree with any instructor asking their students to bring it all in one form, even though this is where we are officially done with getting the derivative. But as I said, if any instructor is asking his or her students to simplify something like this, or put it all in one fraction, I agree totally, because it looks completely awkward to write an expression like that, especially having that 0 there. So our final concluded one is simply, and so notice 0 plus 1 over x is simply just 1 over x. So multiplying 1 over x with all that expression here is 1 over. We have an x here, and then in parentheses 1 plus natural log of x. We are done with our final expression of our derivative. So that was already our final derivative, but here's the final form, the final expression, where things look a little more simplified. Okay. And so that's how we find derivatives of logarithms. So let me erase this part C and let's try another one for here. And then we can also have something as following. We can have a function as y equals, let's say, natural log of x, but now I'm raising that to the 5th power or something like that. Okay, and so what I see now is that I can recommend taking natural log of x right here as the inside this time. So I'm gonna say let a variable u be a natural log of x, even though, as I said, there is no right or wrong. It's just what I recommend here, simply because I've found it. This is the best one for me, but you can find another one. Who knows? It works better than mine. Okay, and so now once we substituted the natural log of x for a variable u, then the outside here, this is whatever that the function remains looking like after we substitute this natural log of x away. So your function now, overall function, appears to be u to the 5th power. Okay, so outside function is the 5th power function, and inside of that variable we sort of dumped in that expression natural log of x, and that's how we've been having that concept about inside and outside the whole time ever since we learned about the chain rule. So now the chain rule, again, I just said the chain rule, so we're about to use the chain rule to solve our problem. So chain rule says, now finding this derivative, we have to take the derivative of the outside, okay, and the outside here can just simply be the power rule. So now I'm going to write 5 times, instead of u, see, technically it's 5u to the 4th power, okay, but instead of writing u, now I'm going to write the actual expression of u right there. So that's the derivative of the outside, and now I am going to multiply, okay, with the derivative of the inside. So my derivative of the inside, how about I'm going to turn it into one more extra step right here. It's only an indicator that in the next step I am going to actually find the derivative of this. So this just straight out from the chain rule, and then now we're looking at 5 times natural log of x. Sometimes I don't have to be too picky about using parentheses. So natural log of x all raised to the 4th power, and now I'm going to multiply. The derivative of natural log of x is 1 over x. Okay, and here officially we're done with finding the derivative. So I'm okay if my students leaving me something like this. However, but I can change my mind too. I can change my mind too. So my students, you got to watch out for this. But also there will be instructors, I'm pretty sure there will be instructor asking students to put this final expression as one expression. So it's going to be 5 times the natural log of x all to the 4th and divided by x. So this final form does look a lot shorter. Okay, and that's how we found the derivative of this function right here in part D.